The standard deviation isn't so easy to read off the histogram, but if the histogram has a bell shape, then you can read the standard deviation directly from the histogram. If the histogram is bell-shaped, then the average is at the center of the histogram, and the standard deviation is the distance between the average and the points of inflection on either side. Let's see this in a demo. Let's look at the histogram of maternal height in the births data. It's a nice symmetric distribution here, and we could try to estimate the mean and standard deviation directly from the picture. The mean looks like it should be somewhere right about here, maybe say 64. And if you trace down from the top of the histogram, you can trace out a curve that's very smooth and has a point of inflection right about here, say at 61. It looks like the standard deviation is the distance between 61 and say 64. The distance from the point of inflection to the center. That's about 3. Let's check to see whether our estimates are correct. Yeah, the mean height is 64.05 inches, and the standard deviation is just a little bit less than 3. Pretty good. Let's look at birth weights and see if we can do the same thing. We've got the bell-shaped histogram for birth weights. The average seems to be right in the center at about 120 ounces. And if you draw a smooth curve going down to the left, you see that the point of inflection sits probably about at 100. So the difference between the point of inflection and the center, 20 in this case, is the standard deviation. The standard deviation should be 20 ounces. Let's check to see if our answers are correct. Yeah, the mean weight is about 120 ounces, and the standard deviation is, well, 18 ounces, close to 20. Pretty good for eyeballing it. So when we have a bell-shaped distribution, it's easy to see the mean and standard deviation directly from the bell-shaped distribution itself. Bell-shaped distributions are often modeled with the normal distribution. The standard normal curve is a curve that has a very complicated equation. It's shown here, and you can see a lot of your favorite numbers showing up here, pi and Euler's constant and others, but we're actually not going to use this equation very often in our course. Every normal curve, every bell-shaped curve can be related to this standard normal curve. The standard normal curve looks like this. This is the bell-shaped distribution that we're always talking about. Notice that the center of the standard normal curve is at 0, and the points of inflection are at -1 and 1, precisely 1 standard deviation away from the center. Let's look at normal proportions. You might be curious, how big are most of the values in a normal distribution? Well, Chebyshev showed that no matter what the shape of the distribution, the bulk of the data are in the range, the average plus or minus a few standard deviations. We saw that if you went out as far as 5 standard deviations on either side, you should capture at least 96% of the data. If a histogram is bell-shaped, then almost all of the data are within 3 standard deviations of the average. Here's a chart that shows some of the bounds on distributions and how they relate to the bounds on normal distributions. In general, you get very weak bounds to about all distributions. For instance, within 1 standard deviation for just an arbitrary distribution, you really can't guarantee any observations. But for a normal distribution, you can guarantee about 68% of the observations will lie within 1 standard deviation of the average. For an arbitrary distribution, you can guarantee that at least 75% of the observations lie within 2 standard deviations of the average. But for a normal distribution, you get a much higher percentage, a much higher proportion. 95% of the observations lie within 2 standard deviations of the average. And within 3 standard deviations, in general, we can only guarantee about 89%, whereas for the normal distribution, well over 99% of the observations should lie within 3 standard deviations. A key area is the area between -2 standard deviations and 2 standard deviations above the mean. Within 2 standard units of the origin, we expect to find 95% of the area in a normal curve. Normal curves are ubiquitous. They show up all over the place. They arise in a lot of practical applications of statistics. Let's just look at a few. The birth weights of babies follow a normal distribution. The sales of shoes for women follow a normal distribution. The heights of men and women follow normal distributions. Even the lengths of deer antlers captured in some hunting expeditions follow a normal distribution. Why is the normal distribution so common? Some of the mystery is dispelled by the central limit theorem. The central limit theorem is an important theorem in probability. It says that if the sample is large and drawn at random with replacement, then regardless of the distribution of the population, the probability distribution of the sample sum, or the sample average, is roughly normal. It's roughly bell-shaped. Even if the distribution of the original sample, the original population, was highly non-normal. Let's have a look at this in the demo. The central limit theorem tells you exactly what happens when we look at the distribution of sample averages in any distribution. We'll explore this with a very skewed distribution, the flight delays experienced by United Airlines flights in 2015. First, let's load the data from the United Summer 2015 CSV file that you can find on Day28. Here's the data. You can see the date, the flight number, the destination, and the delay. This flight was delayed almost 4 hours. This flight left 3 minutes early, and this flight wasn't delayed at all. The delay is in minutes. Let's try to graph the histogram. You can see that the histogram has a huge tail that goes all the way to the right. Most of the observations are actually negative for the delay, but some of them are very, very large. The mean and standard deviation of the delays give a rough sense of the center and spread of the distribution, but not its shape. The mean delay is just a bit over 16 minutes, and the standard deviation of the delays is about 39 minutes. Note that the median is much less than the mean, characteristic of a right-skewed distribution, since the few high values for delays pull the mean to the right, but not the median. The median here is just 2. That means that half the United flights left 2 minutes or less late, and half of them left 2 minutes or more late. Let's take 10,000 samples, each of size 400, and store the sample averages in the array means 400. Let's just do that. This could take a moment or two. What we're doing is we're gathering up 10,000 different samples and calculating the sample averages. Remember, the central limit theorem says that the sample averages should obey a bell-shaped distribution. Here's a little picture of a bell, and it looks kind of like a normal curve. Let's put those sample averages into a table and compute the histogram. Here's the histogram. Remember, the population average for all United flights had an average delay of 16.65 minutes. And here you see the distribution of the 10,000 sample size 400 sample averages. And you can see that the average of the sample averages looks like it's right on about 16.65 minutes. In fact, the population mean and the mean of the sample averages in this case are nearly identical, 16.64 versus 16.65. The central limit theorem says roughly that as the number of observations in a sample gets larger, as 400 becomes 900 or 1600, etc., the distribution of the sample averages becomes bell-shaped with the same mean as the population mean. Moreover, the function describing the bell-shaped curve can be written down explicitly. It depends on the population mean for the center, and it depends on both the population standard deviation and the sample size for the width of the bell, or the standard deviation of the sample average. The sample size need not be so large. We don't need to have 400 observations. We see this effect even when the sample size is only about 60. The central limit theorem is a very important theorem in probability and statistics, and we'll be applying it in the following classes.